The silicon-vacancy center in diamond has recently been demonstrated as an optically accessible solid-state qubit. This color center consists of a silicon atom taking the place of two carbon atoms in the diamond lattice, and it has a characteristic bright optical transition at 737 nanometers. At low temperature, this transition shows nearly lifetime limited line width and is spectrally stable over multiple hours, allowing efficient, indistinguishable photon generation from distinct silicon vacancy centers. Improving the coherence time of any solid-state qubit that has access to this coherent transition would be a critical advance for quantum communication applications. By measuring the temperature dependence of the optical line width, ground state relaxation time, and optical transition energies, we have gained insight into the processes that limit spin coherence times in the silicon vacancy center. The ground and excited states both have E-symmetry and form orbital doublets with a spin-orbit splitting of about 50 and 250 GHz respectively. With photoluminescence excitation spectra taken below 30 Kelvin, we measured the optical transition line width, and in the same temperature range we used pulsed fluorescence experiments to determine the ground state relaxation time. Both processes showed a linear temperature dependence that indicates a single phonon orbital relaxation process within the ground and excited states. At temperatures above 50 Kelvin, the optical line width showed a cubic dependence on temperature. This trend, and other temperature variations measured for silicon vacancy, are accounted for by a second-order electron phonon dephasing process. We have developed a consistent microscopic model of the phonon processes that describes both the single phonon mechanism, dominant below 20 Kelvin, and the two-phonon dephasing that takes over at higher temperatures. The longest orbital relaxation time in the ground state, measured at 5 Kelvin, was about 40 nanoseconds. Our model indicates this orbital relaxation should dephase any spin coherence formed in the ground state, accounting for the recently measured coherence times on the order of 40 nanoseconds. By identifying the orbital relaxation mechanism at low temperature to be dominated by single phonon transitions, we are able to suggest techniques to extend this coherence time. Reducing the temperature would decrease the phonon occupancy at the transition energy of about 50 GHz. Based on the measured scaling, we expect an electronic spin coherence time of 1 microsecond at 1 Kelvin and up to 1 millisecond at 260 millikelvin. A different approach would involve eliminating the availability of 50 GHz phonons by suppressing the phonon density of states at this frequency. This may be achievable by fabricating phononic structures directly into diamond material, similar to what has been done for photonic structures. An easier approach, however, is to use the silicon vacancy centers present in nanodiamonds that are too small to support the 50 GHz acoustic phonons, which have a wavelength of about 250 nanometers. It is an intriguing possibility that color centers in nanodiamonds, which usually show inferior properties compared to centers in bulk diamond, might prove to have valuably extended coherence times.